We'll now continue with section 5.4, talking about properties of logarithms and their applications. We'll begin with what is called the change of base formula. Recall that we have discussed the fact that only certain logs can be entered into the calculator. Remember that the calculator would allow us to calculate a log base 10 of a number. So we could easily, for example, put in our calculator log base 10 of 5 and get an answer. The calculator also allows us to do log base e. Remember that log base e is really written as the natural log of 5. So we can do those two bases in our calculator. But anything else, for example, if our problem had said log base 7 of 3, that is not something that we can enter in the calculator. And so change of base gives us a way to evaluate logs that look like this. And so it says let a and b both be positive real numbers, neither of them equal to 1, and let x be a positive real number. Then log base b of x is the same thing as log base a of x divided by log base a of b. Now that can be a little bit confusing with all of your letters, but it's actually very easy. What it means is that you are going to take this expression, for example, the one that we have here, log base 7 of 3, and you're going to write it log of 3 divided by log of 7. And you are free to choose the base that you want as long as you choose the same base on the top as on the bottom. But remember that we want to be able to put it in the calculator. So the only base that really makes sense to use is going to be a base 10. All right, and so we can enter that in our calculator and come up with an answer, and we'll do that in the next examples. But again, just a rearrangement of terms. Okay, so let's begin with our first example, which is log base 7 of 15, and we want to apply that change of base formula. And so we are going to write this as log of 15 divided by log of 7. And again, just a rearrangement, you're going to do your 15 on the top and the 7 on the bottom. You choose the base, so we could choose a base 10. All right, and when you plug that in your calculator, you are going to get 1.392. And as always, if you have trouble putting that in your calculator, please feel free to email me and ask. You do not have to put the base 10 in, so you simply enter it in as log 15 divided by log 7. All right, so moving on to our next problem. We have log base 1/2 of 3. I'll give the computer just a second to catch up there. Okay, so second problem, log base 1/2 of 3. We'll rewrite it as log 3 divided by log 1/2. And so again, we're going to enter this in our calculator, and we're assuming a base 10, even though you don't actually enter in the base 10 in your calculator. So we'll enter in log 3 divided by log 1/2, and we're going to end up with a negative 1.585. Our last one is log base pi of 5. So again, we're going to say log 5 divided by log pi. That's your change of base. You can choose whatever base you want, but again, it only makes sense really to choose a base 10 so that you can use your calculator on both of the top and the bottom. You enter that in your calculator, log 5 divided by log pi, and you should get 1.406. So again, change of base gives you a way to evaluate these logs that are not in base 10 or base e. All right, so we're going to move now to some applications of the log functions. We're going to look at 3 different applications. One is pH. So it says that the pH of a solution is defined to be, and we're going to kind of want to remember this expression. This is kind of our formula, negative log, and it's then H sub 3 O positive, where that H sub 3 O positive is the concentration of hydronium ions in units of moles per liter. Solutions with a pH less than 7 are said to be acidic, while those with a pH greater than 7 are basic. And we've got a chart given in the book. You certainly don't have to know this, but just to kind of show you some pH values for common solutions. All right, so let's look at an example. We have a sample of orange juice is determined to have a H sub 3 O positive concentration of 1.58 minus 10 to the negative 4 moles per liter. What is its pH? Okay, so if we go back to our formula, we know that pH is this expression that I circled here. Okay, so I'm going to write that down just so that we've kind of got that in front of us. That pH is equal to negative log, and then H sub 3 O positive. Okay, so this one is worked out for us, and we're just going to kind of follow along. What they have basically done is they've taken this 1.58 times 10 to the negative 4. They're telling me that that's the H sub 3 0 concentration. So we're going to take that 1.58 times 10 to the negative 4, and we're going to plug it into the formula right here. Okay, and so that's what we're seeing down here that they've done. They've plugged that value in. And then that is going to be something that we're going to just plug into our calculator. So negative log of this 1.58 times 10 to the negative 4. You're going to get negative, and then the part inside the parenthesis with the log is going to be negative 3.80. On your calculator, the two negatives are going to be a positive 3.8. Okay, so you can see that's a very easy application of how we use the logs to calculate pH. Okay, after doing the calculation, you see that the reason for the minus sign is pretty apparent, because if you want your pH to be comparable to other pH values, then you want it to be positive. And so that's why we're multiplying by -1. They're just making that note. All right, so another common application for logs is earthquake intensity and the Richter scale. So in the formula, we have I sub 0, which is the intensity of a just discernible earthquake. I is the intensity of an earthquake being analyzed, and R is its ranking on the Richter scale. And so our formula is R is equal to log I over I sub 0. And the Richter scale, you may or may not know this, if you have an earthquake that is classified as small, it has a value of less than 4.5. If it's moderate, the value is between 4.5 and 5.5. Large, between 5.5 and 6.5. Major, between 6.5 and 7.5. And finally, greatest are those that are greater than or equal to 7.5. All right, so let's look at an example. The January 2001 earthquake in India was 80 million times as intense as a 0-level earthquake. What was the Richter ranking of this devastating event? So again, let's get our formula down. We'll write it right up here so that we can kind of see it. We've got the log of I divided by I sub 0. Okay, and so we're going to let I, which is the intensity of the earthquake that we're looking at right now, this January 2001 earthquake, that earthquake was 80 million times as intense as a 0-level earthquake. So the 0-level earthquake would be sort of that just discernible earthquake. And so we're doing 80 million times as intense as that. All right, so they're going to say, let's let I, the intensity of this earthquake, be 80 million times a 0-level earthquake. And so that's where we're getting this. Okay, and so we're going to plug that in for the I in our formula, and you'll see that on the next slide. Sorry, right there. All right, so we have our formula, which had said R is equal to log of I over I sub 0. All right, so here's the I that we had on the other screen, and then we're going to have the I sub 0 on the bottom from the formula, and R is equal to log. So look at what happens here. These I sub 0s, they cancel out, and the 80 million they've written as a scientific notation problem. So 8 times 10 to the 7th. Remember that that's the same thing, because if you take 8 and multiply it by 10 to the 7th, you move your decimal place 7 places to the right. 1, 2, 3, 4, 5, 6, 7. and add in those zeros. All right, sorry, got a comma right there. So you see that that's the 80 million. Remember, you have a property of the logs. It says if you have two things that are multiplied together, you can break it up with a plus. So we got log 8 plus log base 10 of 7, or log 10 to the 7th. Now, really, at any point here, you could put this in your calculator. And I would probably suggest going ahead right here and typing in your calculator, log 8 plus log 10 to the 7th, and you should end up with that 7.9. So remember that if it was greater than 7.5, it was considered a greatest earthquake on that Richter scale. All right, and then the final application that we're going to look at is that of a decibel scale. So talking about sound, again, I sub 0 is the intensity of a just discernible sound. I is the intensity of the sound that you're looking at, and D is the decibel level. So you have a similar formula here. D is equal to 10 times log of I over I sub 0. All right, and how do we compare decibels? 0 is barely discernible, to 40 is the level of a normal conversation, 80 is the sound of heavy traffic, 120 for a loud rock concert, and finally to around 160. At 160, you would likely rupture your eardrum. So our example says, given that I sub 0 is 10 to the negative 12 watts per meter squared, what is the decibel level of jet airliners engines at a distance of 45 meters for which the sound intensity is 50 watts per meter? So the intensity of this current sound that we're looking at is 50 watts per meter. That's my I. We are given the I sub 0. And so we pretty much have exactly what we need to plug into this formula. Remember that your formula from the previous screen was D is equal to 10 log I over I sub 0. So we know what to plug in for the I. We're going to do the 50. We know what to plug into the I sub 0. We're going to do the 10 to the negative 12th, and then we're just going to calculate. And so you can see that that's been done here for you. All right, so we have 10 log, we've plugged in the 50, we've got 10 to the negative 12th. And again, you can really go ahead and plug in your calculator right there if you'd like. You could certainly simplify it the way that they've done, but you could take it from this point straight to there with using your calculator. All right, and so you should come up with 137. And so this would not be ear splitting, but it would be very painful because it would be close to that ruptured eardrum level of 160.